Welcome. This is the review lecture on probability theory for machine learning. So what is probability theory? Probability theory is the study of uncertainty, and as you know, uncertainty is all around us. Probability theory is a mathematical attempt to formalize this notion of uncertainty that we have. Mathematical probability theory is actually based on measure theory. Measure theory is a much more general setup where you try to assign any kind of measure to a set. So a measure could be, for example, the volume of a set, but it could also be a probability, and that's where the link between measure theory and probability theory can be found. But this is a very deep and profound level, and we will not work down there, but we will work at a much higher level so that we can work with it throughout the course. What we will do is the following. We will introduce and review the formal language to talk about uncertainty. That's all we are going to need throughout the course. The upcoming slides, they're mostly based on an article that you can find on the internet. It's called Review of Probability Theory, and you can find it under the link that is given in the PDF of these slides. So what is it that we're going to do in probability theory? Well, probability theory is concerned with data generating processes. What is a data generating process? Well, you could think of a coin, for example. If you toss a coin, you're actually generating data because when the experiment is over, you either have a data point which says heads or one which says tails, and you can repeat this experiment and generate more data. But that's a very simple example. There are much more complex examples possible. Think, for example, of a weather system or EMG data from muscles. Now, what probability theory is about is taking one of these data generating processes and reasoning about what the outcomes might be or what properties they're going to have. And there is some kind of dual concept to this, and that's what statistics is all about. That is, you're given the data from a data generating process and you don't know anything about this process, and you're trying to infer information from the data about the generating process. That's the opposite direction. And this process is called statistical inference. If we revisit the examples we just talked about, you can, for example, ask the question whether the coin is fair or not. Or you could try to find some climate change in the weather system data that you get. Or you could also try to reason about whether the muscle was contracting or not during the data that you have. And that's what statistical inference is about. Inferring or deriving conclusions from premises. And the premises in our case, that's the data. Now the point is that statistics is what we're interested in. Machine learning is a part of statistical inference. But statistics uses the formal language established by probability theory, and that's why it's worth studying probability theory in the first place. Now let's dive into probability theory. The first thing we're going to study is the concept of a probability space. A probability space was introduced by Kolmogorov in 1933, a Russian mathematician, and it's based on the work done in the roughly 40 years before that. So in mathematical terms, that's a very short history actually. A probability space consists of three basic elements. These elements we're going to study now. The first element is the sample space, which is usually denoted by a capital omega. Here. Omega is the set of all outcomes of a random experiment. So let's pick an example. If you roll a die, and it's a normal die, then it has 6 faces, 1 to 6, and that's the set of all outcomes omega. But you could also think of a setting where you roll the die twice, and then if you care about the order, you get the following set of outcomes, namely omega prime, which is the set product of omega with itself. So it's all tuples with two numbers from 1 to 6. So actually what we have is that omega prime has 36 elements. Now, usually we're not really interested in single outcomes, but groups of outcomes with a certain pattern. And these groups of outcomes, we will call them events. And events will be sets of outcomes. So an event is a subset of omega, the set of outcomes. And the set of all possible events will be denoted by a calligraphic F. So it's all possible events. And that's a subset of the power set of omega. The power set is the set of all subsets. Maybe you're familiar with this concept. However, we cannot choose any F that we like. It has to have some structure so that we can reason about it. We need to have some axioms to define which events are possible or not. Namely, the first axiom is that the empty set has to be a possible event. And this basically means that we're assuming that this is not empty. So we know that the empty set is an F, so F itself is not the empty set. The second axiom says that if you have an event A that is in the sigma field F, then also the counter event omega without A has to be a possible event. So if something is possible, then the counter event is also possible. And the third one says, if you have a couple of events, A1, A2, and so on and so forth, that are possible, they are in the set of possible events, then if you take the union of them, this is also a possible event. That is to say, if I can look at two or more events individually, then I can of course also look at them jointly. These three axioms is what we require. And now we're going to have an example of an event. And events usually come with some wording. So, for example, we can say the die outcome is even. That's an event. And this we can transform into a set. It's the set of all small omegas in capital omega, so all outcomes where the outcome is even. And that's 2, 4, or 6, obviously. And now the smallest sigma field that contains this particular event that the die outcome is even is the one that is depicted here, the one with the empty set, with the full set, with the event that we have, and the counter event. So let's quickly check the axioms. We have to have that the empty set is in F. Well, that's true. We have to have for each A in F that the counter event is also in F. If we check this, for the empty set, it's the full set, it's in there, that's fine. And vice versa as well. And for 1, 3, 5, the counter event is 2, 4, 6, and that's in the set, and vice versa, 2, 4, 6, and 1, 3, 5. So the second axiom is fine as well. Now the third one, if I take any set and take another set, and I take the union of these, then it has to be in F as well. So if we take the empty set, that's boring because it doesn't change anything. If we take 1, 3, 5, there's only one set that is not the full set left, and that's 2, 4, 6. And if we take the union, then it's also an F, and that's fine. So this set F that is depicted in the last line is actually a sigma field, but it's just the smallest sigma field. You could also take the power set of omega, so all subsets of omega, and that would be a valid sigma field as well. Now, You might ask the question, if I can take the power set, why don't I just do it? Why do we make it so complicated and take these small sigma fields? Well, the problem is we would have to go down deep into measure theory to actually see why we need to do this. The problem is that for uncountable sets, like the real numbers, for example, this approach will fail. We will not be able to define probabilities properly if we always take the power set. And that's why we need these axioms. These axioms ensure some kind of standard that we know about the events, or the structure of the events. Now, we're introducing the third element of a probability space. We've had the set of outcomes, capital Omega, and the set of events, calligraphic F. And the third element is the probability measure, because we are dealing with probability theory, so somehow we have to get probabilities. And the probability measure is simply a function, and it maps an event to a probability. So that's where the events come back in. Probabilities are defined on events, not on outcomes. Of course, you can have an event that contains only one outcome, and through this proxy you're going to get a probability for a certain outcome, but probabilities are defined on events only. And in order to define probabilities properly, we're going to have axioms of probability. And these actually are the ones that go back to Kolmogorov. The first axiom is that a probability is non-negative. Well, that sounds reasonable. For any event that we have, the probability is non-negative. It can be zero, but it's not negative. The second one is the normalizing axiom. That is to say, the full set, omega, all outcomes taken together, they have a probability of 1 or 100%. The third axiom that we have is actually already about calculations. So if we have several events, A1, A2 and so on, and if they are disjoint, that is to say these events, they don't share any outcome, then we can calculate the probability in the following way. So we take the union of these events, and the probability of this can be calculated by summing up the individual probabilities of the individual events. Let's look at an example. If we take a die and the event A1 is again the event that the die outcome is even, and the event A2 is the event that the die outcome is odd, then obviously these two, they are disjoint. And then we can calculate the probability of A1 union A2 by summing up the probabilities of the individual events. We have just defined some axioms for a probability measure, but we haven't actually defined any specific probability measure. That's why we're going to look at an example now. In the case of rolling a die, there is actually a very simple probability measure that can be applied. That's the one that you're familiar with if you've done any statistics before. And that is, you get the probability for an event A simply by considering the number of outcomes and comparing them to the number of possible outcomes. So you divide the number of valid outcomes for this event by the number of all possible outcomes. And that's obviously a number between 0 and 1. And you can try to prove that it fulfills these three axioms. Now we have defined all three elements of a probability space. Let's repeat them. The first element here, that's capital omega, and that's the set of all outcomes, as opposed to calligraphic F, which is the set of all events. And the third element and most important element is the probability measure, which maps events to a number between 0 and 1, which we then identify as a probability. That's the basic element we're going to work with. That's a probability space. On the previous slide we had some very simple axioms. Think of the last axiom we talked about. It said something about disjoint events only. So in all the axioms we were talking about, there were no sets that were intersecting each other. But as it turns out, the axioms that we defined, they're sufficient to prove a lot of other important properties. And some of these properties are listed here. Let's go through them one by one. The first property that you can prove is that if you have two sets of outcomes, two events, A and B, and if the event A is contained in the event B, then the probability of the larger event B is at least as high as the probability of the smaller event A. Well, that sounds reasonable. We have more possible outcomes, so the probability must be at least as high. Now the second property also concerns two events, A and B, and we're trying to look at the intersection between A and B. And there's going to be a shorthand notation for the intersection of events, because that's something we're going to use a lot throughout the lecture and throughout this video. And that's simply P of A comma B instead of this intersection symbol. It's just a shorthand notation, but it means exactly the same. Now if we intersect the two events, then we know that this intersection is contained both in A and in B. And consequently, the probability of this intersection can be at least as high as the minimum of the probabilities of A and B, because it has to be contained in the smaller set, and from the first property that we proved, we can derive that this statement must be true. The third property that you can prove is concerned with unions. We again have the two events A and B, and we're looking at the probability of the union. How can we calculate this, or can we say anything about this? And what you can prove is that it is at most as big as the probabilities of the two individual events. And the problem is, why do we have a smaller or equal, less than or equal sign? That's because we count outcomes twice, potentially, because some outcomes might be in A and in B, and we would count them several times when it comes to probabilities. Now the fourth property tells you something about counter events. So if you know the probability of the event A, then you can easily calculate the probability of the counter event omega without A by subtracting the probability of A from 1. So 1 minus P of A is the probability of the counter event. And what this tells you is if the event A happens with a probability of 20%, well then the probability of A not happening is 80%. They sum up to 100%. That matches our intuition. The last property on this slide is the so-called law of total probability. And in math, whenever a theorem or a property has a special name, then it's probably important. And the law of total probability will come up a couple of times throughout this video and the lecture. Well, let's look at it. We again have disjoint events A1 through AK, so K different disjoint events. And this time they're even more than just disjoint. They're a partition of the set of outcomes omega. A partition means not only that they are disjoint, but also that if you take the union, then you arrive at the full set. And what the law of total probability tells us is that if we sum up the individual probabilities of these disjoint events, well, then we arrive at one. And this makes sense because every outcome is contained in exactly one of these events A1 through AK, because it's a partition, and through this it's counted exactly once, and every outcome is counted, so we should arrive at a probability of 1. But you can prove this rigorously if you want to. It's not exactly obvious why you would want to prove this, but you'll see that it's quite a natural and quite a helpful property that we're going to need again and again. We will not prove any of these important properties here, but I strongly recommend to you, if you have never worked with proofs or with probability before, to try to prove these. It's not too hard. Just look at the axioms and apply them in the right order and you will arrive at these properties.